Well, welcome everyone. It's really great to see this room filled up. My name is Sally Wilson. I am a biology faculty member here at the college. I also have taught agriculture courses in the past, and we just are reintroducing our horticulture program here. It was my privilege to know Tom Colbert. About 10 years ago, I had a student who wanted to take honors courses and get an honors degree. And I didn't know anything about that program, and Tom was the advisor. And so I went to him and we talked about how to generate some new interest in our honors program. And he retired not long after that, and he handed that over to me. So I had the privilege of working closely with Tom on that and some other projects. And it's in his honor and in honor of Professor Shearer, who many decades prior had been a professor, and Tom had started this symposium in his honor, and so we're carrying this on in honor of both of those professors, in order to bring in people with expertise and a passion for particular topics that might be interesting to our community and our students and our faculty and staff. So it's my great pleasure to invite you here and invite you to come back in April for our next speaker in the symposium series. This is our second. We'll have 3, and then next year we'll repeat our symposium again. And so if you have some suggestions or ideas for topics that you'd like to see us cover, or speakers that you would like us to consider inviting, we would love to hear from you. I'm going to now have our Professor P.J. Colbert, Tom's widow, is going to speak today and introduce our guest, who she actually knew previously and suggested to bring Professor Gutowski.
Thank you, Sally. You know, the introduction is wonderful, and I just have to acknowledge your role in reviving this year's symposium. You know, it was really kind of your idea to do this. It wouldn't have happened without your inspiration and your enthusiasm. I also want to recognize the financial contributions of the Martha Ellen Ty Foundation and the MCC Student Senate, and also to Dr. Robin Lilienthal, our provost, Michelle Frost in the marketing department, and the continuing education and plant services staff. You make running these programs a team event. Thank you so much. It's good to see some former faculty here. Some of you may have been in attendance 35 years ago when Tom started this year's symposium. I see Ed Jackson, he might have been. Conrad DeJardin, for whom this hall is named. And also the faculty and staff and community members who are here interested in this program. Thank you for coming. So it's my pleasure to introduce Dr. William Gutowski, whose lecture is entitled Our Changing Climate, Directions and Choices. Dr. Gutowski is a professor of meteorology at Iowa State and a member of the United Nations Intergovernmental Panel on Climate Change, and was awarded the Nobel Peace Prize with this panel in 2007. Professor Gutowski received his PhD in meteorology from MIT in 1984. He's a fellow of the American Meteorological Society. You have to learn that if you're a meteorological.
It's part of the test. And it's going to be on your test later on.
He has served on national and international programs such as the World Meteorological Organization's World Climate Research Program that have guided the course of climate research. His work has had special focus on changing climate in regions of the world such as Africa, the Arctic, and the United States. He's also co-authored reports on climate for the United States National Academy of Science. Clearly, his research on climate change has earned him global recognition. So let's give a warm welcome to Professor Gutowski.
Thank you. Thank you, PJ, for that really gracious introduction. I'd have to say that, let me get this started. Good. It's a real honor for me to be here today to continue the legacy of this symposium and the two people who carried it forth through the years and have continued carrying it forth. And it's great to see this wonderfully diverse audience here, because we need all of you to be involved in dealing with the future that's presented to us of climate change, as I'll come back to later. So yes, I'll talk a little bit about directions, but also choices, and choices that we all need to be thinking about, choices that we can make as we go farther forward in time. I also want to acknowledge some of my colleagues at Iowa State and other places who have contributed some of the information that I will be presenting today, particularly Gene Tockley, who has spoken in this forum before, but also Chris Anderson and Daryl Hertzman, who were or still are at Iowa State, and then a couple of other people at other institutions around the world, Michael Weiner and Jan Sedlacek. So there's some key messages that I'd like you to take away with you from what I show today. One is that we know very clearly that humans are causing an increase in greenhouse gases, and this is causing more energy in the form of heat to accumulate in the Earth's climate system. And so as a consequence, we are changing our climate, but we have choices. As I'll show, there are implications of what this means, but there are also choices that we can make in all this to basically try to control our future as best we can, and especially for our children and our children's children and further generations, thinking farther ahead. So what I'm going to be talking about here, I'll start off talking about what has happened to give you some background. I will talk about what the future holds from all of this and some implications for the upper Midwest where we live, and then I'll start talking about our choices and how we work together to work on those choices. So what has been happening? Well, a basic fact coming out of all this, as I've already said, is our planet is heating up. And we know this from many different perspectives. First of all, the global temperature is rising. I'll come back to these figures a little bit later, but basically they show temperatures averaged over the planet as a whole going back to the mid-1800s. And there's generally an upward trend, especially in the more recent decades. But that's not the only thing. Most glaciers are melting. What this figure is showing results of is the cumulative loss of ice from glaciers measured around the world, and what that means for sea level rise. When that water melts, it's got to go somewhere. What's been happening is it's been going into the oceans, causing sea level to go up. The Arctic Ocean ice is shrinking. The Arctic is the part of the planet that is heating up the most, roughly twice as fast as the rest of the planet. And you can also tell, if you look at this, it's not just a steady downward trend. This is the September sea ice, which is when the ice is at its minimum extent throughout the year. But if you look at any other month of the year, you'd see the same basic pattern. And you would also notice that it's not, again, a steady downward trend. There's a lot of fluctuations from one year to the next, because the weather has lots of fluctuations in it, as we know from here living in Iowa, thinking about one winter compared to a previous winter. Sea level, as I've already said, is rising. It's rising because those glaciers are melting, but also there's heat being stored in the ocean, and that added heat causes the water to expand ever so slightly. But when you've got an ocean that is somewhere on the order of 2 miles or more deep on average going around the world, any little expansion shows up as a significant rise in the level of the ocean. And the growing season here in Iowa is getting longer here and across America. So this dot here shows the date of the last significant frost in the springtime, going back quite a few years, going back to the 19th century. And it's a really, you can see again, there's a lot of fluctuations from one year to the next. There's an upward trend shown by this line. But again, the weather in any given location always has all sorts of variability to it that we also have to think about when we're talking about climate change. But there is a general upward trend, and farmers have been responding to that. Farmers don't always want to acknowledge that, oh, well, maybe climate's changing, but they've been responding to it. There's also been improvements in agricultural technology, particularly in the seeds that are made hardier for springtime growth. But the growing season has been getting longer because they can plant earlier, and farmers have been doing that. So there's a lot of local changes that occur. This is just one example of sea level rise, just to bring the point home even more so. This doesn't affect us directly, thankfully, but in Miami they have these occasional king tides, and they can cause flooding on nice sunny day, so they get these so-called blue sky flooding. This line here is where if the tide is higher than that, you'll get flooding. And the blue colors here show how often that occurred in 1996. You go forward to 2019, and now it's occurring much, much more frequently. And so you can have these bright blue sunny days, and cars are having to drive around downtown Miami, and floodwaters from the sea level rising up, and even on clear days. So it's not even when there's heavy rains causing floods. So this is happening in coastal areas around the country and even around the world. So I want to come back to these global average temperatures. This diagram here, these little solid lines show the 10-year average or decadal average of temperature has been measured. This is averaged over the whole planet, going back to 1850 and going farther forward in time. There was a period where things were just kind of fluctuating up and down a little bit. There was this rise in the early part of the 20th century, which I'm not sure really had a lot to do with the increase in greenhouse gases. It might have had more to do with changes in the output coming from the sun. And then it leveled off for a while, partly because the heating from the sun kind of leveled off. And we also had substantial industrialization going on during this period that put a lot of pollutants into the atmosphere, which actually can have a bit of a cooling effect. But then the real greenhouse effects started to show up, things that accumulated so much that these later decades going into now the 21st century, in my mind, clearly show the impact of increasing greenhouse gases on our climate. And the warmest years, these little dots, if you can see them, are the individual years. The two warmest years were 2015 and 2016 in this record, when there was this phenomenon called an El Nino, which tends to be a warmer period overall. But I would point out, among other things, that a previous record high at one time was way back in 1998 when there was a strong El Nino, and all these subsequent later years did not have strong El Ninos, but they caught up to 1998 and have even surpassed it. This past year was not an El Nino year, but we had the third, according to this record, the third warmest year on record. So temperatures are going up substantially, and there's a clear upward trend in all this. The past decade was the warmest, and we don't know what's going to happen with the next coming decade, but decade by decade, over the past 50 years or so, temperatures have been going up and up and up and up, and I think we have a clear physical understanding as to why that's happening. It's not just numbers. All those pictures I showed you early on, if it was just one of those things happening by themselves, you'd say, well, that's interesting, that's kind of a curiosity. But when you see them all together, and you say, why is all this happening? You come down to just one simple explanation, which is that, yes, the greenhouse gases are causing heat to accumulate in our climate system. They all point in the same direction. And that heat is accumulating, especially in the oceans. We don't have records in the oceans that go deep ocean, that go as far back in time, but from 1970 forward, this shows the heat that's been accumulating in different parts of our climate system. These two parts here are parts of the ocean, the upper ocean and the deep ocean. The atmosphere and land are just these very thin slivers down here. And so that's kind of fortunate for us, because what it means is that the oceans are absorbing a lot of that excess heat right now, but it's still accumulating, and it's maybe causing a lag in how much things could be warming up, but the heat is there. And eventually that heat's going to start to percolate into the rest of the climate system. So we've had this buffering from the oceans, but the oceans just can't keep holding it back. We've seen that the atmospheric temperatures have been going up anyway. So we know the energy is increasing in our climate system. But it's also important to recognize, I talked about fluctuations in time, that it's not just a steady trend always in one direction. It's also not a steady change going on everywhere evenly. I mentioned that the Arctic is heating at roughly twice the rate as the rest of the planet. Even here in Iowa, we don't necessarily have the same warming going on as some other parts of the world sometimes. This shows the average temperature increase for 2019 compared to a baseline, which was the average temperatures from 1961 to 1990. And what you see, if you look at the scale over here, is actually compared to that 61 to 90 baseline, 1990 was actually, for where we are, was actually a little bit cooler than that baseline, even though for most of the rest of the planet, 1990 was much warmer than that baseline. There's other things that go on when climate is changing. It's about temperature, but there's other things that happen as well. And as I'll show you in the next few slides, part of what's going on is that warmer climate has been causing more moisture to come into the upper Midwest, moisture coming especially from the Gulf of Mexico, which feeds a lot of moisture into our region and does a nice job supporting our agriculture. But that moisture has been increasing, and so that means we've had more cloud cover, which tends to retard the heating by the sun. We've had more rainfall. That water falls on the land, it evaporates off the land, and that tends to have a cooling effect as well. So there's other changes that go on at the same time, and it's important to step back and make sure you're looking at the whole climate system and not viewing it as just purely temperature, even though that added heat is clearly the driving factor in all of this. So here's an example. This is the yearly precipitation for Marshalltown, Iowa. It's very nice. They got a very nice set of records that go all the way back to 1893. And I've got two different colors here. The darker colors are for years that were above the long-term average of about 40 inches. And the lighter colors are for years where they were below that long-term average. And you see that those darker colors start to accumulate as we go toward the end of the 21st century and end of the 20th century and into the 21st century. And in fact, if you ask how many times did it exceed 40 inches in different periods, well, in the first 70 years, there were 11 of these events where the precipitation accumulated over the year exceeded 40 inches. And if you go over the final 56 years, there are almost twice as many of these events. So this goes back to the point I was just making, that one of the things that happens where we live when you have this warming going on is we get more moisture pumped into our region, which to a certain extent has been good for our agriculture, but if it keeps doing it more and more, you start to think about flooding and erosion, and maybe it's not quite so good if it starts to increase yet further. But that's one sign of how you have to think about more than just temperature. And obviously when it's raining, again, it's cloudy, so that cloudiness blocks the sunlight from heating us up as much during the day. When there's more water on the ground, there's more water that can evaporate. And if you think about when you step out of a swimming pool in the summertime, you might get an initial little chill because that water evaporating off of you is actually cooling your body. And so the same thing happens here if it's cooling the land surface. This is from Dubuque. I didn't have anything that was comparable for Marshalltown, but this is when that water evaporates, it puts more moisture in the air. So this is showing the dew point temperature, the humidity of the atmosphere. And again, this is going year by year from 1970 forward. The average value is that solid black line. You can see that there are more and more years that are poking up above that average. And this dashed line here is, if you know anything about statistics, it's a fit of a straight line to all of that. And it's just bringing out that upward trend that you can clearly see by just the different color shadings of years that are above or below the average, and that there's many more years above average. And so the humidity is going up. That has all sorts of implications for us, has implications certainly for agriculture. Higher humidity can promote the growth of pathogens on plants, for example. It also can make the air more uncomfortable for us in the summertime if you have a heat wave. And I'll come back to that in a little bit later as well. So there's all these issues that go on with water in various ways, whether it's rainfall, humidity. This also shows, it's a map that shows trends in humidity over a little bit shorter time period, but it gives us the big spatial picture. The blues are where humidity has been trending upwards, and you can see that the Midwest here, it's been getting that substantial increase in humidity, especially compared to other parts of our country. So again, it's all tied in with how the water moves around in our climate system, and it's all been promoted by the increase in temperatures that allow more water to get into the atmosphere. And then this has an impact on the rivers. If you have more rainfall, then the rivers go up. This might be a little bit difficult to understand here, but what's shown is how much water flows in the Cedar River and then the South Skunk River, which is not too far from us, when you have different types of floods. And you may have heard people talk about the 100-year flood, for example, a flood that has a 1% chance of occurring in any given year. So that would be the water levels here above 100. The black line is for this baseline period of 1960 to 2009, and then the blue line is a future projection of what might be occurring, although for some reason they use the years 1960 forward to 2059. I'm not quite sure why they did that kind of an analysis, but the main point is that the strength of those strong floods goes up especially like in the Cedar River, but even here in the South Skunk River where the flow is weaker, you still get this increase. So if you get more rainfall occurring, if you get more moisture coming to where we live, it's more falling out as rain. That rain has to go somewhere. Some of it evaporates back into the atmosphere, increasing the humidity, but a lot of it gets into the rivers, and so the flooding can get stronger as well. So what's causing the changes? Well, I've already told you where I think this is going. Atmospheric concentration of carbon dioxide has been far, far greater than the past 650,000 years, and I think they even have records that go a little bit farther back now that suggest maybe even the past million years it's highest. So these graphs here show, the top one shows carbon dioxide going back 10,000 years before 2005, so essentially before the present. And you see that it's basically a flat line, and then all of a sudden it spikes up when you get up to essentially the present. The inset up there shows the last 150 years or so, just breaking it down a little bit. But the main point is that there's this big upward spike. These other two graphs are for two other greenhouse gases, methane and nitrous oxide. And they also trended along pretty steadily, and then all of a sudden spiked up round about the middle of the 19th century, which is when the industrial period started and was going full force, and when we really started burning fossil fuels, especially coal and then later petroleum, to power our industries. And so there's been this substantial increase going on. And so I would say these are clear signs that humans have caused the increase. We know that this increase makes sense to think that it's caused by fossil fuels, but people who are atmospheric chemists can tell you by the isotopes of these carbon molecules that they clearly are carbon molecules that were part of fossil fuels that got into the atmosphere. And I should say that people can go this far back in time, not because we had somebody out there making measurements, but they do very interesting work with ice cores in Greenland and in Antarctica, where they look at little bubbles of air that got trapped in the ice cores, and they can measure those bubbles of air. And after a lot of careful work, they can determine just how far back in time that air is representative of. And then this leads to, I won't dwell on this too much, but it just shows the temperature changes caused by these different increases. So carbon dioxide is on the top. By itself, it's contributing temperature increase of something about 1.5 degrees. Methane and nitrous oxide and some other gases called halocarbons are also causing an increase. There are some other factors that maybe are causing some decrease. I mentioned the pollution that we put in the air. It's referred to here as aerosols, little particles of which you might call soot that we put in the atmosphere, which actually has a bit of a cooling effect. So that's retarded some of the warming. But you put it all together, and the warming that's gone on from 1950 or from 1980 or even now more recent years is stronger and stronger. The warming effect of that is really important. There's a bit of an irony here in that I mentioned the soot. If we start to reduce the burning of fossil fuels, or at least clean up the fossil fuel burning so it puts less soot in the atmosphere, that could actually promote further warming by cleaning the air, because we're getting rid of those soot particles. But the overall issue is just how much we're putting in the atmosphere in terms of the greenhouse gases. And I also, just as a little side note, I would say this is the result of simulations people have done of the global climate. And there's two general categories. There's the simulations that people do using only natural factors and don't put in any of those human-caused increases in greenhouse gases, and then simulations that include the human factors, essentially the greenhouse gases increasing. And you can see that when you do the simulations with the greenhouse gases increasing, and then you look at the actual temperatures over the 20th century going into the 21st century, you can get that increase at the end of the 20th century. You don't get that increase if you don't include the human factor. And again, it's pointing to that very rapid change occurring at the end of the 20th century as being tied to the greenhouse gases. Things before that, as I said, there may be some other things going on, like changes in how much the sun is heating our planet. That has not contributed to any more of the more recent increase. But this is just the starting point. There's a lot of detailed statistical analysis that people who are experts in this area do to say, yes, the pattern of change that's occurring is clearly a pattern that you would get if you had greenhouse gases increasing in the atmosphere and not some other factor. Okay, so what does the future hold? When we look at the future, of course, we don't know exactly what's going to happen. We only have one planet, so how can we test hypotheses? How can we test whether or not an increase in greenhouse gases is going to cause anything further to happen, or if other things that we do might cause other changes to occur in our climate? There's various ways we do this. We look at the observed behavior. We look at what some other climatic factors over short terms that we've already observed, like volcanic eruptions, which also put soot in the atmosphere, how that affects climate and how the climate system responds. So we have some observational basis for understanding this. We have our computer simulations that tell us how the planet's climate as a whole is changing, these global models. But we also always have to rely on fundamental theory. And I want to emphasize this because it's not like we're just simply packing things into this computer simulation and saying, oh, look what's happening. We have to make sure that it actually makes good physical sense. And so that fundamental theory is very important. And I always point out to people that trying to understand at least the basics of what's causing global warming is not all that complicated. It's basically college freshman level physics, which maybe some of you have taken, or even high school level physics. And I realize not everybody has taken a physics class, but the point here is it's not some obscure rocket science or anything like that. It's really very basic science that very clearly supports everything that I'm talking about here today. And we need to have that basic science. Again, if we simply looked at numbers that we had collected from observations or simply ran these computer simulations, that by itself is not sufficient. We have to make sure that there's a good, solid physical foundation behind it, and we understand it that way. So what does the future hold? Well, again, we don't know exactly what the future might be because a lot of it depends on what we as humans do. So what people do is they construct scenarios about what the greenhouse gases might be like in the future. And two scenarios that people have worked with, especially, these letters are going to seem obscure, but this 8.5 refers to a future scenario that is loosely like business as usual. We keep doing everything as we've always done it, and the greenhouse gases keep accumulating substantially, and that leads to these simulation results here. There's other cases that people look at, perhaps the opposite extreme that people think is maybe a realistic perspective is this one that's labeled 2.6, where you see the temperatures also go up a little bit towards mid-century, but then they start to come down. So these are all based on people trying to make some estimate about what humans might do to control greenhouse gases. What's plotted here is the average temperature of the planet simulated by all these different computer simulations. These computer simulations are not all 100% identical. People have slightly different ideas about how you construct these simulations. And so you get a spread in the results. So this cloud here is a spread about the average of all these different results. But you get a clear separation as you go from the mid-21st century toward the end, based on decisions that humans make, based on decisions that we as a society will make going forward. And so we start to get an understanding that there could be very different changes that might occur. Again, as I said, this one corresponds to what you might call a business as usual kind of situation. This one here corresponds to something that might be akin to these Paris Accords that you've heard people talking about. It's a bit related to that, maybe even a little bit stronger than those accords, but it's something that people feel is a plausible behavior for humans to make. We're certainly not going to just stop burning fossil fuels overnight all of a sudden and it's going to disappear. And we're going to, that just won't happen. We'd be too disruptive, obviously. And in fact, some people even think that this 8.5 scenario might become unrealistic as you go towards the end of the 21st century because they're claiming that the impacts of climate change are going to be so strong that it's going to be really disruptive to society and we just won't be able to keep doing that business as usual behavior. But that's all theoretical for the moment. We see that there are clear pathways that the future can hold. This also has impact on other things. So up on top is that temperature diagram I showed you. This shows the sea ice extent, again, for that month of September when the ice in the Arctic is at its annual lowest ebb. And it decreases substantially in both of these scenarios. In the 8.5 case, by mid-century, it effectively disappears. In the 2.6 case, it also goes down substantially. So there are big changes that can occur even if we start to really have a substantial control on the warming that is occurring. And this is not simply a sort of an interesting factor about the sea ice. there are a lot of native cultures that live along the shores of the Arctic Ocean. They're already experiencing the impacts of climate change in terms of what it means for their lifestyle. And so that points to lots of human impacts that can occur. Of course, another factor with the reduction of Arctic sea ice is people are thinking now about that being a shipping lane, which then has all sorts of other implications, including social implications when you start to have these commercial ports set up along the shores of the Arctic Ocean. But that's outside of my expertise. Another factor here, this says global ocean surface pH, how acidic is the ocean? People don't often think about this, but that carbon dioxide, a lot of it that we put in the atmosphere actually gets put right into the ocean. About half of what we emit every year gets absorbed by the ocean. So that's another way that the oceans have been buffering a lot of what we've been doing. But as you increase the carbon dioxide, that actually starts to make the ocean slightly more acidic. And there's already been measurable impacts of that on sort of plankton, small ocean organisms that have calcium-based shells. And it starts to eat away at their shells. So there's already measurable impacts of that. Going forward in time, you can see that the pH level goes down substantially for that 8.5 case. It starts to level off, very much so for the 2.6 case. That means the ocean becomes much more acidic as we go farther forward in time in that 8.5 case. I'm showing this in part because some people have talked about trying to do some kinds of geoengineering initiatives where maybe you do something to block the sunlight or something like that to counteract the heating from the greenhouse gases. Well, if we keep burning fossil fuels and we do something like that geoengineering, we're still going to be putting more acid, developing more and more acidic oceans, and so that's going to have an impact right at the very foundation of our food chain, something that's very important to think about. And this tends to occur more in the higher latitudes because the higher latitudes can absorb more of that CO2. Think about that can of pop that you might open sometimes. That's got carbon dioxide in it. It holds that carbon dioxide longer when it's cold rather than it's warmer. So the warmer oceans don't hold the CO2 as much as the colder oceans. So it especially has an impact on the ecosystems in the high latitude oceans. And then global mean sea level rise. Again, everything is fitting together in the same picture that if you have that high-end scenario, the sea level rise is even greater than if it's in the low-end scenario, though even with that one, you get an increase. The units here are in meters, so 0.4 meters corresponds to about a little over a foot, foot and a half maybe. And you might say, well, so the ocean goes up a foot, foot and a half, so what? The issue with that is, yes, it can lead to that blue sky flooding I was talking about because that gets added on top of other behaviors. When you have storms going along the coast, it's that much more water that gets pushed ashore. So it has impacts on extreme behavior especially, even if the average is not all that substantial. And then you get things like tropical storms get stronger, so the precipitation falling out of them, and the warmer climate, you tend to get more high intensity precipitation, the dark black curve compared to this lighter curve, which is a more contemporary climate simulation. So the precipitation increases because there's more moisture getting into the atmosphere. When it gets into the atmosphere, then it falls out as rain. So there are choices we have. This shows the average temperature over the planet, the change in temperature at the end of the 21st century compared to more or less the end of the 20th century, with that 2.6 scenario and that 8.5 scenario. These dots just show that it's a significant change by some measure, some statistical analysis that people do. But you can see that it's basically warming everywhere. There's some interesting things that go on with the ocean at the high latitudes just south of Greenland in both of them. But basically it's warming everywhere, and it warms more so over land where we live than over the oceans. But there's a big difference in those colors, as you can see. And so that means, again, that there are choices that we can make. So what are some implications for where we live? Precipitation changes. This is mid-20th century, 21st century compared to the end of the 20th century. This is a slightly different scenario, but it corresponds to that 8.5 scenario. This is from a different formulation of scenarios, but it basically gives the same information. For Iowa, this is the upper Midwest now, the precipitation on average would increase This shows heavy precipitation, and Iowa is kind of spared a bit. Some of these other states have more of heavy precipitation, downpours occurring, at least according to these calculations. And it makes sense that if you get more moisture in the atmosphere, more can accumulate there, and when it rains, it really pours. This shows the wettest 5-day total. So climatology, people oftentimes like to talk about 5-day periods. Why they chose 5 days, I don't know, but they want to say what's accumulated over a certain period of time. And we're kind of spared any significant changes that way as well. But what goes on with this, it seems almost ironic. You can get an increase in the number of consecutive dry days. What's happening here is, if the atmosphere can have more moisture present in it, well, it takes longer for that moisture then to build up to where you can get rain. So it builds up and then it finally releases as a big downpour, but it takes longer to get up to that point. So on average, it seems almost ironic or contradictory. You can actually have more drought and more heavy rainfall occurring because it takes longer for that moisture to build up to produce that substantial rainfall. So we could have more dry periods showing up as well. As I said here on my words off to the side, increased rainfall, heavy precipitation, for us at least about the same, tendency for longer dry periods. All this has lots of implications, of course, for the agriculture in our state. But if the atmosphere is getting warmer and it can basically suck up more moisture into it, more water can evaporate into it, well, that means that the soil moisture, it could well go down. And for that 8.5 case, we see here in the middle of the United States that yes, the soil moisture starts to get drier as we go towards the end of the 21st century. So another big agricultural implication. In fact, if you look around the world, there's lots of areas of significant drying, partly because of reduced precipitation, but also because of increased evaporation from the surface. And then no areas of really significant increase in soil moisture. Where you see those blues, that could be soil moisture increase, but this hatching here says it's not a real clear, significant change. We can't be confident that that's what would really occur there. Closer to home, dangerous heat waves will be more frequent, more severe. This comes from something called the Iowa Climate Statement. This is a statement that gets issued every year that several of us put together. Started back in 2011, and it focuses on a different topic every year. This past year, it was focusing on heat waves. So what that means is we're going to have more days where temperatures, the hottest 5-day period in a year is going to go up substantially to where by mid-21st century, we could get maybe the hottest 5 days averaging over 100 degrees Fahrenheit compared to something that typically has been more like upper or low 90s. And this is perhaps a more dramatic way of rendering that. The number of days per year when the temperature goes above 90 degrees Fahrenheit, 23 days per year back in the historical record. If we go to mid-21st century, we may get something like 2 months of days where the temperature goes above 90 degrees Fahrenheit. And the humidity will have gone up as well. So we're talking about heat waves that could be very dangerous for human health. So these Iowa climate statements have been issued every year since 2011. As I say here, there's various topics that have been part of it. This is just a little sampling. I already talked about the heat events, which were this past year. What this means for designing buildings, talking about the humidity that increases that will occur and the implications of that, but also talking about possible ways of working with agriculture to actually try to mitigate some of those increases and what climate-smart agriculture could do to help reduce the impacts of climate change. So this started out in 2011. There was a letter that we had to the governor, the legislature, and because it was 2011, that was just before the Iowa caucuses in 2012 that year. This is in November of 2011. And it was this letter this is from a report in the Des Moines Register signed by 31 of us from 22 colleges and universities across Iowa. So it was widespread. It wasn't just a small scattering of people. Talked about how we're already experiencing effects of climate change, and they have clear connection to the changes in global climate. So this was almost 10 years ago we were saying that. And additional changes will challenge farmers and planners to maintain the prosperity of our state, especially our agriculture. Moving forward, the changes, as I've already hinted, can have impacts on agriculture. The two people who originally started this were my colleague at Iowa State, Gene Tockley, and then Senator Rob Hogue, senator from over Cedar Rapids. More recently, it's been Senator Joe Bolcom, who's also a faculty member at the University of Iowa, who's been the main spearhead of all this, but Rob continues to be engaged on climate issues as well. So there are a number of us who've been involved with developing these statements over the years. And that first one got a lot of coverage, Des Moines Register, a number of other newspapers around the state, Iowa Public Radio, the American Geophysical Union, one of my professional organizations, gave a thanks to us for issuing this, and other interest groups. And it also got other types of attention, like from blogs. So there's this one blogger said, well, these people think you're stupid. A bunch of academics in Iowa suggest that CO2 has caused intense rainfall to, quote, occur 5 times more often than in our previous history. Well, that statement that we made was based on actual observations, not something that we were just throwing out there. So it got that, but it also got the attention from Comedy Central. I don't think that the Daily Show mentioned it per se, but you probably can't read the words here on their website that said, Iowa scientists beg candidates to please acknowledge reality. And it seems like that's still, unfortunately, a struggle, because I think the science is very solid that, yes, climate is changing and humans are causing it to change. So what are our choices? This little graph here shows along the x-axis is the cumulative total CO2 emitted by humans, anthropogenic CO2, starting in 1870. So just the total accumulation of just what was emitted. Now again, half of this goes into the oceans, but still, how much we've emitted. Over here is the temperature rise averaged over the whole planet starting at the same time. There's 1890, 1950, 1960, 2000, 2010. You see there's pretty much a straight line there, a very direct correlation between the two. And in our simulations, that continues on forward. And where it stops depends on, again, the choices we make. So that 2.6 scenario, it stops with an overall warming of somewhere less than 2 degrees, but as you go to these intermediate scenarios and up to that high-end scenario, you can get an increase of over 4.5 degrees. That's the global average temperature, and you might say, well, again, average temperature 4 degrees, yeah, that might even be kind of nice in the wintertime. But the point is that causes all sorts of other changes to go on, causes the heat waves to increase, as I've mentioned. It causes all those water-related changes that I've talked about to also occur. So there's a lot of impacts that can occur, even though that might not seem like it's such a huge change in itself. But when you average over the planet as a whole, it kind of smooths out a lot of that. So there are choices we can make. Differences in the amount of warming that can occur, and of course that goes right back to that picture I showed you several slides ago. So we need to work together, but not like the thing that's laid out here. What's shown here is an academic researcher, someone in their ivory tower like myself, and I'm doing my work, and I might be doing some stuff talking about rivers, so I'm using this hydrologic model, and I get all sorts of output generated by that, and I share that output with other researchers, and they go, oh, yes, 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 very interesting, and we all talk about it together. But when we try to share that with other people, and this slide comes partly from a project I had several years ago with the Squaw Creek watershed, which is over by Ames. You know, the stakeholders, the public, well, they don't understand what we're talking about. So they'll fall asleep if we're lucky, or they might just walk out on us or whatever. So that's not the way this has to work. What I want to emphasize is that we all have to work together, which is why I'm so happy to see all of you who've shown up here today. So it starts out by working directly with the people in that watershed and learning from them. That we as scientists, it's a little hard sometimes for an academic to actually step back and listen to other people because we want to just talk. But we have to be listening. And there's a lot of words that people have been using lately in my community, talking about co-design, co-exploration, co-development of projects, all about cooperation and working together. If we don't do that, then we don't understand the people we're trying to connect up with. We don't understand their values. We don't understand what really motivates them, what they're going to be responding to, how they see themselves being part of solutions and adaptations. So we have to have that. Then we can do all of our work. We can run these sophisticated computer simulations of various types. And when we do that, then we get results that we can then share back with the people that we've already been talking to, and they can understand us better and we can understand them better. And we have to keep going round and round. It's not just a one-pass thing. This has to be an ongoing, continual dialogue. And ideally, in the course of doing all that, we actually arrive at something that we could call sustainability, something that becomes a viable pathway to the future. But it takes all of us. As the old expression goes, it takes a village. And I think that's really important here because we all bring different talents, different capabilities, different skills to the table, and they're all vital if we as a human society are going to move forward into the future in a way that clearly is sustainable and productive, as I always say, for our children and our children's children and so on down the line. Somebody told me at a presentation I gave a few weeks ago that if you look at at least some Native American cultures, they always talk about thinking about the implications of what you're doing 7 generations into the future. So that long-term perspective, which we often seem to lose, thinking about what the long-term outcomes are of our actions. And that's one aspect, one way to think about it is what are you doing that's going to be affecting people farther along the way? Iowa farmers, at least some of them, actually have a good perspective on that because they think about the legacy of what they've inherited and they think about what they want to pass on to their children and grandchildren. So that's a big step in the right direction. And I think it's an attitude that we all need to be taking as we look at this issue because these are changes that occur over many decades into the future. And so things we're doing now have substantial implications for people in the future. So again, the key messages here are that humans are increasing greenhouse gases. As I've shown, this is causing more energy to accumulate, more heat to accumulate in the climate system, and as a consequence, we are changing our climate, and we will be changing it into the future. But we have choices to make, and to really think through those choices and arrive at what we hope are the best choices, it takes all of us, everybody in this room and everybody in the community surrounding us and everybody around the world. So thank you for your time and your attention. Thank you for coming out today. You know, we do get students engaged in our research on occasion, maybe not as much as we should. There's nothing that there's something that my colleague Gene Tockley has been doing stuff with wind energy and making measurements at wind sites. There might be some opportunities there. We should talk about this further. One of the things we started talking about is the possibility of a climate science major, training people to be able to go out and work with the public. And obviously, Marshalltown Community College is one of the feeders into Iowa State. There'd be great ways of getting people started here that could then feed into that program. So that's one aspect of it. There are people in other disciplines, and I can't speak to their expertise, but people who talk about the so-called bioeconomy and sequestering carbon. We're actually starting a committee on campus to talk about how the campus itself can move towards carbon neutrality, and that's going to involve those people as well. And the more I learn about them, the more there might be other opportunities there. So what I would say is maybe we should try to get some discussion going and talk about those opportunities. You know, I showed you some nice measurements that were done in Marshalltown on precipitation. There's some other things we could talk about doing as well as we go farther forward that would be very, very useful. And a way of getting students engaged. That building up that expertise is obviously very important and very useful. So the question is, what can we do here in the middle of Iowa to decrease our carbon footprint? Little anecdote. Several years ago, I found some software that allowed me to compute my family's carbon footprint. And this was an American family of 3, and our carbon footprint was about the same as a European carbon family of 3, which I thought was pretty good because they're much more energy conservative than we are. And we're in an infrastructure that you just can't, unless you got yourself completely off the grid, you can't just reduce it to 0. But that was
before I put in all my business travel doing climate research, which blew it out of the water. But the point here is things we can do. As always, you can always try to be more efficient with the energy that you use. Try to think carefully about, okay, do I really need to go driving my car off there? Or if I'm buying a new car, is it possible to buy a car that's more energy efficient? Some other things, you know, it gets into some personal choices, and you have to think carefully about what works for you. There is, you know, what temperature you keep your house at. My daughter used to complain that we always kept our house too cold, and when she grew up, she was going to move off to Hawaii. She hasn't done that. But personal choices like that are important. What you use for light bulbs is important. Remembering to turn off lights when you're not really using them. Turning off your TV when you're not really watching it. Those are all individual choices you can make that can actually, you know, it can help you. You're spending less on energy, but it also contributes to just reducing the demand for energy as well. Work with community groups to promote the development of alternative sources of energy. In Ames, there's an effort now to get a solar farm going, which would be one example. Wind energy has grown substantially over the past 10 years, so much so that it's actually causing some tensions now, which I understand. Sometimes these wind farms have been put into place without maybe really having all the appropriate community involvement that's needed. So those things have to be worked through so that you don't get a backlash. And so that's where working with community groups can play an important role. Talking with your neighbors, writing to your members of Congress. I try to do that myself. Sometimes I imagine they're getting tired of hearing from me, but they need to know that people out there view this as an important issue. And businesses will respond. I was talking with somebody the other day about just one example, plant-based protein, substitutes for ground beef. I myself can't tell the difference between it. Maybe some people can. And if you don't like the plant-based stuff, fine, that's the choice you can make. But that has a smaller carbon footprint. And businesses are now responding to that. You see that McDonald's and Burger King are responding to that. And that means that the businesses that supply them are responding to it. And so that's going to have implications for our agriculture as well. So there's individual choices you can make that come into play, as well as making sure that your elected representatives know about all this. Another aspect of this is that something I try to mention whenever I can is, a lot of people are more conservative, usually react against environmental things because they think, oh, it's all about government regulations and government intruding on my life. Well, if you think about it, there's a lot of technical innovation that is needed for all of this. And so there's great opportunities for entrepreneurship, and the government needs to be working hand in hand with the business community to promote that. Because if we don't do it, it's going to happen elsewhere in the world. And we do have a competitive edge in some of these areas right now, but China's putting a lot of effort into this. Other places around the world are. We should be promoting those business opportunities for people as well through incentives or other means. But it really, again, it takes the whole community to be doing this. There are various educational programs that have cropped up for teachers to go, just like this example, to go to far-flung places, see the environmental concerns and the impacts of changing climate, and then they have real on-the-ground experience. I'm pretty jealous of her opportunity because that's the last continent I haven't been to. And
like $15,000 for 10 days,
yeah.
Like that.
No, it's great because you're there for a real scientific purpose. And so, yeah, it was a wonderful opportunity. And especially, it's changed, the climate is changing there too. I'd mentioned the Arctic, but you may have heard in the news recently that there's a record high temperature recently in Antarctica. I think it got up to 65 degrees Fahrenheit, which is just incredible to think about for Antarctica. It's on that peninsula that juts out towards South America, so it's not right on the heart of Antarctica. But there are related things going on. Antarctica now is starting to lose, on average, ice mass as well, which is contributing to sea level rise. Greenland has been losing ice mass on average for some time now, which is also contributing to sea level rise. So all these changes have global implications, even if they're local. So what she's seeing in Antarctica is really important for just putting all of that into a context that where it actually affects us. So how are we going to make an investment to have a meaningful impact? Well, but when we sent people to the moon, it was one nation doing it on our own. We're talking about a global program. And again, there's little things that everybody can do. It's not like, when we sent people to the moon, you couldn't do anything really as an individual to promote that other than pay your taxes and maybe buy Tang every so often or something like that because they drank that. But all these things that I mentioned earlier are different types of activities that also contribute to it. And there's not necessarily a very clear-cut dollars and cents thing you put on it. But those are also important. Certainly the governments around the world have to come together and work in accord with each other, I think, to arrive at an understanding of what needs to be done and what our targets are for reducing greenhouse gas emissions. But again, that's where the private sector becomes an important player in all this. So it's not even a matter of necessarily government investment, but it's also investment into the private sector as well, which individuals can do. And it's also, again, your own individual actions. So yeah, maybe the net effect is something like that, but it's not like we're just putting out a tax and saying, well, we're going to collect all this money and then we're going to distribute it. There's all sorts of people that are engaged in this. And there's all sorts of private philanthropic foundations that are engaged in this issue as well. But we all have to make sure that we have a clear sense of what that direction is and the ways that we can work together as a global community. Yes, the question was algae farms and how they may pull carbon dioxide out of the atmosphere because they're basically plants like trees and they just pull the CO2 out of the atmosphere. Could that be done on a widespread basis? I'm not the one to answer that question. I know there's research going on at Iowa State in that whole direction. People are trying to think about a carbon neutral economy or reducing carbon emissions or the net carbon dioxide in the atmosphere. Hypothetically, it seems quite plausible. Once you have something to do with that carbon after you take it out of the atmosphere, you can't just let the algae decay and then put carbon dioxide or methane back into the atmosphere. Same thing is with trees. People talk about growing trees. Well, of course, once you grow the tree, you've got to do something with the carbon that's stored there. You don't just burn the tree. So there's a further aspect of it, but it can be part of the solution, as I understand it. But again, I'm not an expert in that area, so don't take my answer as the final word. But there are people at Iowa State who are doing research on that. Yeah, thank you very much for coming.